Unit 4.8 complex number. So the class objective, we have two things we want to achieve: to identify, graph, and perform operations with complex numbers. The next one is to find the complex number solutions of a quadratic equation. So here are a couple things we have to pay attention to in this. First, operations means the addition, subtraction, multiplication, and division. In the division part of complex numbers, we have to learn one more concept, which is complex conjugate. Then we can use complex conjugates to factor. So let's take a look of what complex numbers are. So complex numbers consist of two elements. The first one is the real part, which is A here, the real part, which is a real number. And the second part is the imaginary number, which consists of two things. B itself is a real number, and I is the imaginary unit. So let me give you an example of a complex number. Say 2 plus 4i. So 2 is the real part, which is a real number. 4 is also a real number, and I is the imaginary unit. Now let's take a look at what imaginary unit is. As we all know, when we take the square of any real number, we always end up a positive real number. For example, if I say 2 square, which is equal to 4, of course it's positive. Or if we say negative 2 whole square, we still got 4, which is also a positive real number. So anything we take the square is always a positive. But is there anything that we can take a square of it and become a negative number? And in math, the answer is yes. And mathematicians come up with imaginary unit I. And when we take the square of it, it's actually equal to negative 1. Or we can say the square root of negative 1 equal to I. And they represent the same thing. Now let me give you an example. So square root of negative 9 basically equal to square root 9 times square root of negative 1. Or we can simplify to, okay, let me move this away. So we can simplify this one to square root 9 equal to 3 and square root of negative 1 equal to I. Now let's take a look at another example. So basically, they're doing the same thing as what I just showed it to you. And right here, so we start from square root of negative 18, and they try to simplify to make it square root of negative 1 times square root of 18. Right now they change this one because square root of negative 1 basically equal to I, and square root of 18 right here we can change it to 9 times 2, which is equal to square root of 9 times square root of 2, and that's why you end up getting this, because square root of 9 is equal to 3. So that's the final answer. So let's start working on the operations of complex numbers. Let's start with the addition and subtraction of complex numbers. Basically, the operation is the same as what we do with our variables. So here's the examples. So 4 minus 3i plus 4 minus 4 plus 3i. So just think about these are x. So what they do is they try to combine the like terms right here, okay, which is the imaginary part of the complex number, and here's the real part of the complex numbers. So they just add them together, which is 0. minus 3i plus 3i, just like minus 3x plus 3x. So this is the addition part. And when we do what? The subtraction part is the same thing, but this time you have to pay attention to the what? To the sign change, because it's a -1 times a positive, so end up we have a -1. So we take away the parentheses, we got 5 minus 3i plus 2 minus 4i. So again, they combine the like terms here. Just watch out the sign, then you'll be fine. These two are the real part, so you end up having 7 minus 7i. Done. Next is the multiplication of complex numbers. Basically, when you do multiplication of a complex number, you do exactly as you would do with multiplication of binomials. Let me give an example. Let's start with the simple one first, which is a. And again, I'll get my pencil. So we do the distribution. So 3i times -5, we got -15i. And then 3i times plus 2i, we got 6i squared. So watch out, I squared means by definition equal to -1, and we didn't do anything with this one, so we keep it. Now they switch the position because the general rule of thumb when you write a complex number, we always start with the real number part first, which in this case is -6, and then the imaginary part. And in this case, we have -15i. So that's why they write -6 minus 59. The next example is going to be B. So we do the FOIL things by doing this. So 4 times -1, we got -4 right here. And then we have 4 times -2i, we got -8i. Let me change the color so you can see it easier. So we change to blue. So the next is plus 3i times -1, which we have -3i, and then plus 3i times -2i, we have minus 6i squared. So watch out here now. I squared basically, like I said before, is equal to -1. That's why you change I squared to -1. Now we just combine the like terms. So -8i plus 3i, we have -11i. And then for this one, we got -1 times 6, we end up getting plus 6. So plus 6 minus 4, we got 2. So C is the same logic. The last operation of complex numbers is going to be the division. But before we go to the divisions, we have to learn one concept first, which is the complex conjugates. So the definition of complex conjugates is the opposite of the imaginary part of the complex number. Let me give you some examples. So here are the examples, 3 examples. So what I want you to focus on is the imaginary part right here. So this is the regular complex number, and its conjugate is gonna be what? The inverse of the complex number. So take a look. For plus I, they're gonna change to minus I. For 7i, they change to -7i. For -4i, they change to 4i. But take a look of the what? The real part, they didn't change the real part. So please pay attention to that. Now that we know the concept of complex conjugates, we can start working on the division of the complex numbers. Let's take a look at these 2 examples. The first one, A. 9 plus 12i divided by 3i. So the key here is we have to find the complex conjugate of the denominator. In this case, is equal to -3i. And then we're gonna multiply negative 3i over negative 3i because this expression basically equal to 1. Anything times 1 is going to be equal to itself. So we didn't change a thing by doing this. But by doing that, we can come up with this because this is negative 3i times negative 3i. You got these things. And then on the top, on the numerator position, we do the distribution. So 3i times plus 12i, we have negative 36i. And negative 3i times 9, we got negative 27i. And the next thing is, when you see I squared, we can change it to negative 1. Same here, I squared, we're going to have negative 1. And then we're going to simplify the whole thing. We end up getting 4 minus 3i. Done. Now is the example B. 2 plus 3i divided by 1 minus 4i. We are going to do the same thing. First, we have to determine the conjugate, the complex conjugate of the denominator right here. So 1 minus 4i, the complex conjugate is going to be equal to 1 plus 4i. Now we're going to times 1 plus 4i over 1 plus 4i because this whole expression is equal to 1. Anything times 1 will be equal to itself, so we didn't change a thing here. But by doing this, we can change the denominator become a real number. Take a look at this. So we do the following things again. So 1 times 1, which is equal to 1 here. And then 1 times 4i, we have 4i right here. Negative 4i times 1, you got negative 4i. The last one, negative 4i times plus 4i, we have negative 6i squared. Again, when you see I squared, we substitute it with negative 1, same here. So you end up getting these expressions. And then we do the simplification, and then we're going to end up getting the answer. Done. We can also use complex conjugates to do factoring. So here's the example. So they ask you to factor 2x squared plus 32. So the first step that you want to do is to find the greatest common factor. In this case, is 2. So by factoring out, we got this expression, 2 times x squared plus 16. And then we make use of this formula to factor x squared plus 16 because x squared plus 15, we can change it to x plus 4 squared. So we can change it to x plus 4i according to the formula x minus 4i. That's what I have here. Then we're done.